billion solar masses lands right on top of the heavier mass determination from stellar motions. And so this actually will also help resolve a discrepancy that can lead to better mass determinations for other more distant black holes when we can't actually see the shadow. So getting to the impact of this is important because M87's huge black hole mass makes it really a monster, even by supermassive black hole standards. So you're basically looking at a supermassive black hole that's almost the size of our entire solar system. And in fact, that's part of the reason that we can see it, even though it's so far away. But if we now zoom back out to the more cosmic perspective of the host galaxy of this black hole, the galaxy is made of billions of solar systems, and so on those scales, the black hole itself is minimally small. It's about 100 million times smaller than the galaxy. And if it were a dormant black hole, like the supermassive black hole in the center of our own galaxy, Sagittarius A star, then the galaxy would really have no way of knowing it's there and would basically be just like a pebble in a shoe. But when a black hole is what we call activated by gravitationally capturing material, it starts to convert that fuel into other forms of energy with an efficiency that can be almost 100 times better than nuclear fusion that powers the stars like our sun. And so when that happens in these active phases, black holes temporarily become the most powerful engines in the universe. And they go very quickly from being a pebble in the shoe to a thorn in the side of the galaxy, literally. And the thorns in this case being the jets that Avery was mentioning. In the most extreme cases, these jets can actually penetrate through the entire galaxy and well beyond. But the power that's coming out, we can't see with our own eyes. So if we want to understand them, we have to look in other wavelengths. So we look with telescopes across the electromagnetic spectrum. So I'm going to give you an example of this. This is another very active black hole system, and it's a combined image. So you see in white from NASA's Hubble telescope, the elliptical galaxy Hercules A in the center, and then overlaid in blue is the radio waves from the National Science Foundation's Very Large Array. And these radio waves are basically tracing magnetic fields in space. So this tells us that these jets are just enormous fountains of magnetized material that are being sprayed out from the black hole, not the black hole itself, but near the black hole, nearly at the speed of light. And these particular jets are 100 million times bigger than the black hole that launches them. Now, if we add another layer, we're going to look in the X-rays now from NASA's Chandra telescope, and X-rays are probing extremely hot gas, like billions of degrees. So we're seeing the entire system is embedded in a halo of hot gas, and we can use this information to calculate how much energy the jets had to have to bore through all this material. And what we find is that the jets are carrying the equivalent of 10 billion supernova in energy deposited over one of these active cycles. So this is, these kind of interactions are basically very important because this tiny black hole on these scales is somehow launching these structures and also managing to heat the gas to prevent stars from forming. And since galaxies grow by forming more stars, this has the effect of truncating galaxy growth. And we think it's through these types of interactions that black holes help shape the largest structures, galaxies and clusters of galaxies, and make them look the way they do today. Now, M87 is in a much more modest active state, but as you can see, this is also from Hubble. It's still managing to launch pretty magnificent jets, and these jets are emitting across the electromagnetic spectrum as well, so we need this information to be able to fully understand the system. But if we zoom way out now to the cluster of galaxy scales, this is another combined image where you see red in radio and blue in X-ray. You see just a mess of structures, and we think this is telling us about M87's black holes' past interactions really affecting the cluster scales on time scales of hundreds or tens of hundreds of millions of years. So until now, well, we always thought that black holes were behind these large structures driving these engines, but we never knew. And now with EHT, we have direct evidence of the root of these problems, and we can look at this, and we can now start to make, to understand, combining strong gravity, magnetic fields, and looking at atomic level processes to understand how these processes interplay and conspire to make these enormous structures that are basically affecting the largest scales of the universe. And so to capture all of this information, we need to combine our observations with those across the multi-wavelength spectrum. And so, as you heard from Dan, there's a lot of complexity in these observations, and we added to that by doing a complicated Sudoku of coordination with many facilities across the globe and also in space. And this is similar to the campaign that was run with LIGO for gravitational waves. It's very important to combine signals, both from photons and particles. And so by doing this, we expect that EHT, an active role in this new era of international multi-messenger astronomy. So anyway, looking to the future, the same observations that we took in 2017 that for M87 also included this dormant black hole in our galactic center, Sagittarius A star. And by looking at two black holes at opposite extremes of this activity range, especially combining this with multi-wavelength information, we can better understand the ebb and flow of influence of black holes in the long course of our history in the universe. Anyway, so thank you very much. I'm going to hand this back over to Shep, who's going to say a few words.
Thank you, everyone. I just want to point out that when we first started the Event Horizon Telescope project, the group was small, and I think it had to be small and nimble to carry out precursor experiments and develop the first kinds of techniques and instrumentation that enabled us to move the field forward. But over the past decade, the greatest accomplishment has been the building of a team. As I said before, we're now 200 people strong, many institutes, over 20 countries and regions. And if you want to reduce petabytes of data, if you want to develop new imaging algorithms, if you want to image a black hole, then you need a large team. And it has included many early career scientists, senior scientists, and many of them are here with us today. So I'd like to ask everyone who's associated with the Event Horizon Telescope to please stand up so that everybody in the media can see who has done this work. It's a true pleasure and privilege to work with this crew. And I urge all the media to please go seek them out to learn how the sausage was actually made, how the black holes were actually imaged. I also want to say something in particular about funding and support. This has been a high risk but high payoff endeavor. Sometimes you have to kiss a lot of frogs before you get the prints, before you get the black hole image. And you need supporters, you need funders who will stand by you for long periods of time, who take the long view, who understand that basic science never goes out of style, and who also understand that basic science, you never know when it's going to pay off, but ultimately it usually does, and that you have to play the long game. And we had wonderful partners with the National Science Foundation, with our international funding agencies and foundations, and our hat is off to them for sticking by us for so long. And we look forward to greater things with the EHT as we build out the capability and we continue to sharpen our focus on black holes. Thank you.
Thank you all very much. One note before we take questions. Several of our panelists and many of their EHT collaborators will appear this week in a documentary which has followed the efforts of the EHT for the past 2 years. The film will show viewers just how Shep Doeleman and his team reached the groundbreaking moment. The documentary is called Black Hole Hunters, and it will premiere this Friday, April 12th at 9 p.m. Eastern on Smithsonian Channel. We will now take questions from the audience until 10 a.m. Please raise your hand, wait for a microphone, and identify yourself and who you are with before asking your question.
Seth Borenstein, The Associated Press. A two-part question, please. First, this is M87. You had 2 targets initially. Have you seen anything, have you captured any images of Sagittarius A yet and just haven't released them because for whatever reason? Or have you not gotten those images? And second, one of the keys I understand, Andre guesses, when you look at for this, is this distinct edge of the photon ring. You know, not being a scientist, this